We talk about work all the time, right? Hard work, working out, going to work. But what if I told you that from a physics point of view, most of that stuff isn't actually work at all? Yeah, it's kind of wild. The scientific definition is super specific, and it's probably not what you think. So let's dive in. Okay, let's kick things off with a little thought experiment. I want you to imagine you're pushing against a solid brick wall. I mean, you're giving it everything you've got. Your muscles are screaming, you're sweating. It feels like the hardest work you've ever done. But here's the question. According to physics, are you doing any work? Nope, not a single bit. From a physicist's perspective, you have done precisely zero work on that wall. It doesn't matter how exhausted you feel. So, what gives? How can all that effort count for nothing? And that right there is the first big idea we need to wrap our heads around. In science, work has absolutely nothing to do with how much effort you feel like you're putting in. It's a really specific physical process. It's all about what you actually accomplish, not just how hard you're trying. So, okay, if it's not about effort, then what is it about? Well, it turns out there are two and only two key ingredients for work to happen in the scientific sense. And if you're missing even one of them, you've done absolutely no work, period. All right, ingredient number one, force. This one's pretty straightforward, right? A force is just a push or a pull on something. So, back to our brick wall example, you were definitely applying a force, no question about it. So, check, we've got the first ingredient. But, and this is the big one, here's the second absolutely critical ingredient, distance. The object that you're pushing or pulling has to move. And it can't just move in any old direction, it has to move in the direction of the force. And that was the missing piece with the brick wall. You pushed, but it didn't budge. Not even a tiny bit. Let's look at another example that really nails this down. Imagine you're trying to push a car that's stuck deep in the mud. You're pushing with all your might. So you've got force, check. But the car isn't moving. So distance is zero. That means, you guessed it, zero scientific work. But now, what if you push and the car actually starts to roll forward? Aha! Now you've got force and you've got distance. That is scientific work. Okay, so we have our two ingredients, force and distance. Now we can actually put them together in a really simple but super powerful formula that lets us calculate exactly how much work is being done. And here it is, in all its glory. Work equals force times distance. That's it. It's honestly that simple. If you want to know how much work was done, you just multiply the amount of force you applied by the distance the object moved. Let's use a real-world example to see this in action. Say you're lifting a heavy bag of groceries. Step one, you have to apply a force to lift it up, right? Let's say that force is 20 newtons. That's just the sciencey unit for force. And step two, you lift it a certain distance, maybe 1 meter, from the floor up to your kitchen counter. So to find the work, you just calculate 20 newtons multiplied by 1 meter. And what does that give us? 20 joules. Now, a joule is the official unit for measuring work. But, and this is really, really important, it's also the unit we use for measuring energy. And believe me, that is not a coincidence. This is where things get really interesting. Because when we say we did 20 joules of work, what does that number actually mean? What did we accomplish? Well, it turns out that when we're calculating work, what we're really doing is calculating something way more fundamental, a change in energy. Just think about it for a second. We did 20 joules of work on that grocery bag. So what actually changed? That number, 20 joules, isn't just a result of a math problem. It represents a real physical change that happened to the bag itself. And here is the absolute heart of the matter. Mechanical work done is equal to the energy transferred. They're basically two sides of the same coin. When you do work on an object, you are literally transferring energy to it. This is the big takeaway, right here. Work equals delta E. The work you do on something is equal to the change in its energy. So those 20 joules of work we calculated, that wasn't just some abstract number. It was a literal physical transfer of 20 joules of energy from your body into that grocery bag. Just take a look at this. Before you lifted the bag, when it was sitting on the floor, it had a certain amount of potential energy. But after you did 20 joules of work to get it up onto the counter, guess what? Its potential energy went up by exactly 20 joules. You literally transferred that energy into the bag by doing work on it. Okay, so let's pull all this together and recap the big ideas. Because understanding what work really is, in a scientific sense, isn't just about passing a physics test. It's Well, it's fundamental to understanding how energy moves and flows through our entire world. So, what are the crucial points to walk away with? First, scientific work requires both force and distance. You can't have one without the other. Second, calculating it is simple. W equals F times D. And third, and this is the most important part, doing work on an object changes its energy. In fact, work is the transfer of energy. And this all leads to a really cool final thought. If lifting a book gives that book energy, where did that energy come from? Well, it came from you. You transferred it. So the next question is, where did your body get the energy to give away in the first place? And that, my friends, is a question that connects physics directly to biology and probably to whatever you had for lunch. Thanks for tuning in.